All right, so this is lesson 3. We're going to learn about power and efficiency. So first, power. So think of this. We've learned about energy in terms of joules. Now, if you go to a store and buy a light bulb, right? Radiant energy is measured in joules, just like any other energy. When you buy a light bulb, it says things like watt, 60 watt, 80 watt, 100 watt, 20 watt. Okay, why does it not tell you the energy in joules? And that's because the wattage is the power. So power is how much energy, I have the equation over here, how much energy you use over a certain time period. And that's more important. You can't sell a light bulb and whoever's selling the light bulb specifically say how much energy you're going to use, because how much energy you use depends on how long you actually have the light bulb turned on every day. And you should be turning it off to save to save energy. But power makes a lot more sense. So when we say 20 watts, that means that light bulb uses 20 joules of energy every second. Okay, so power is measured in watts, and we give it the symbol capital W, and 1 watt is the same as 1 joule per second. Okay, now because change in energy is the same as work, we can also say that power equals work over time. And I actually had a friend whose name was Power, and he was always getting upset because his boss was making him work overtime. Now, of course, there are other units of energy. One that most people are familiar with are kilocalories. And you buy like a candy, and you look at it, and it says how many kilocalories it is. Like, oh no. And that is a unit of energy. It's not a standard unit of energy, because the standard unit of energy is joule, but 1 kilocalorie would be equal to 4.187 kilojoules. So it's a lot of energy, especially inside things that have a lot of sugar. Next thing I want to talk about is efficiency. So we have different types of light bulbs. Right? You have incandescent light bulbs. Incandescent light bulbs simply glow because they're brought to extremely high temperatures. In fact, like 1,000, 2,000 degrees, right? Which is why you shouldn't be touching them. When they get that hot, they glow. But if what you want is light, that's a huge waste, because you're creating mostly thermal energy, right? Not light. And so the efficiency is very, very bad. So efficiency depends on what you want. For example, if you were to plug in a stereo, I'm assuming what you want is sound energy. Usually we don't want heat. Usually heat is lost, but sometimes we do want heat, right? Maybe on a blow dryer, we want heat. Okay, so when you're calculating efficiency, your efficiency is the energy you get out, or I should really say the useful energy that you get out of something, over the energy that you put into it. So let's go back to the incandescent light bulb. You plug in an incandescent light bulb and you pay the electric bill for it, so you put a certain amount of electrical energy into that light bulb. The useful energy you get out is light energy. Right? And it's only about 5% efficient. Incandescent light bulbs are terribly inefficient. You could try going to CFLs, the compact fluorescent light bulbs. They're more efficient, but they have mercury vapor inside of them. So that mercury vapor sends electricity through it, and it excites the atoms. And then those atoms, when they drop down from their excitation level, emit UV light. And we don't want UV light. So there's a coating around it, a fluorescent coating, that absorbs the UV light, the high energy light, and over time slowly emits the lower energy light, which would be visible. They're a lot more efficient, but because they have that mercury in them, you have to dispose of them properly. You can't just throw them out in the garbage. And that brings us to LEDs. Those are the most efficient. If you want to know specifically how LEDs work, I do teach that in grade 12 physics. We do a lab with LEDs. But basically you have two semiconductors where one has an excess of electrons and the other has a deficit of electrons. So when the electrons move from one semiconductor to the other, they fall in energy level. And that difference in energy level then gets emitted as light. Very little loss to things like heat. So those are extremely efficient. Okay. All right, so another thing I want to look at is this unit here, the kilowatt hour. So let's go back to our power equation. Power, which is in watts, I'm just going to look at the units here, equals change in energy, which is in joules, over time, which is in seconds. So if I rearrange this equation, right, I can rearrange by multiplying time to both sides, so you get power times time equals our change in energy. Or, from the perspective of units, watts times seconds equals joules. So a watt second is a unit of energy. It's kind of confusing because over here we have this unit kilowatt hour. But kilowatt hour is no different than watt seconds, other than different magnitudes really. Watts you change to a kilowatt, and seconds you change to an hour, but those are still a unit of power times a unit of time. And so this is actually a unit of energy. Now it's a unit of energy you'll usually see on your electricity bill if you ever look at that, because it looks at how much energy you've used in a certain month. And if you use joules, those numbers are going to be huge, right? Because you'll see 1 kilowatt hour is the same as 3.6 times 10 to the power of 6 joules. So you use a lot of energy in a house over the course of a month. So your electricity bill will, instead of having huge numbers that scare you, will use smaller numbers with a different unit. So going over our first problem, here we have a 510 kilogram prize-winning pumpkin raised from the ground to a truck platform, a distance of 1.1 meters, by a machine developed by a group of, hey, good job. Now the action takes 3.2 seconds. So let's draw what's happening. Here we have the ground, and we have a truck over here, and here's the platform. So we take a pumpkin and raise it up to the platform, which is a height of 1.1 meters from the ground. So the ground will label to be a height of 0. Remember, we can choose that. All right, and we know its mass, 510 kilograms. Now it says determine the power of this machine. So we have a machine lifted up that high. Well, power is change in energy over time. Now you have to look at this. What energy is being changed? Well, if we're lifting something, we're changing its gravitational potential energy. It's being increased in stored energy due to the object's position in a gravitational field. So the energy that's being changed is gravitational potential. So this is going to be mg times our change in height, all over by time. And we know all of these. So mass is 510 kilograms. Okay. I'm assuming we're on Earth here, so 9.81 newtons per kilogram. Our change in height, final minus initial, so 1.1 minus 0, that's just 1.1. All divided by the time it takes to raise it, which they tell us is 3.2 seconds. And that'll give us power. So let's see what we get. So 510 times 9.81 times 1.1 divided by 3.2. So 1.72 times 10 to the 3 joules per, joules per second. And a joule per second we write as what? Yes, that's right. Watts. Sorry, another bad joke. Now, part B says, what is the horsepower of this machine? So horsepower is another unit of power. It's not the standard unit of power, but it's a commonly used unit of power. The reason why it's called horsepower, and it's a huge misconception. A lot of people think 1 horsepower is the power 1 horse has. That's not true. So the reason why it's called horsepower is, I can't remember who did this, but somebody used a horse to be able to lift something with a pulley up off the ground and hold it there. And then he labeled that amount of power 1 horsepower. But 1 horse is actually capable of, can't remember, between probably 15 and 25 horsepowers. So 1 horsepower is not the maximum power a horse can exert. The person who just created the definition of horsepower used a horse in sort of like the apparatus of his experiment. That's why it's called a horsepower. And 1 horsepower is equal to 746 watts. So if we wanted to figure out how many horsepowers our machine was, all we'd have to do then is take our answer and divide by 746 watts. So our machine has 2.3 horsepowers. Yeah, so I mean, if you take 20 horsepowers and multiply by 746, yeah, about 15,000 watts. Number 2 says, a fuel-powered loader, raises a 2,200 kilogram load from the ground to a loading platform, which is 2.7 meters above the ground. So same thing. Right? We're changing our gravitational potential energy by lifting something up. Then it says the loader consumes 150,000 joules of energy from the fuel. Okay, so that's how much input our loader actually requires. So first, determine the work done by the loader. Okay, work is change in energy. You can think of it in 2 ways. You can do force times displacement, where you have to equal the force of gravity to be able to lift something, and that's mg, and displacement is h, mgh. Or you can think of it just in terms of the change in gravitational potential, which is also mgh. So however you want to think about it, you end up with the same equation. So the mass of what we're loading is 2,200 kilograms multiplied by 9.81 newtons per kilogram times by our change in height, which is said to be 2.7 meters. Okay, so let's see what that is. Times 1 times 2.7, we get, I'm going to keep all the numbers for now, because we're going to need this for part B. So 558,271.4 joules. Then part B says, what's the efficiency of the loader? So the work done, which is the change in energy, that's what we get out of it. So that also is our energy out. The energy that we put in is what the machine requires, and that's given in the question as 150,000. So our efficiency then is the energy out over the energy in. If you want to change that to a percentage, you just multiply by 100%. Okay, so energy out is 58,271.4 1,271.4. Energy in is 150,000. Multiplying by 100%, and we get 38.8 or 39%. So it's 39% efficiency, which is not too bad. Large machines will have a lot of moving parts. Those moving parts will have frictional forces, and frictional forces produce thermal energy. So a lot of energy is lost to heat.